These are notes on work, energy, and power calculations and equations, and they're found in Chapter 6 of your book. Make sure as you're doing them that you do the calculation before looking at the answer so you can see how well you understand them. So the first equation is work, and that's in Chapter 6, Section 1. Work equals force times distance. So it's the amount of force you exert on an object over a certain distance. So if you have a force of 5 newtons and a distance of 12 meters, go ahead, pause the video, and calculate the work. You should have gotten work is 5 newtons times 12 meters, which equals 60 joules. Work, like energy, is measured in joules, and I'll show you how that kind of all pulls together in a second. Remember that through Newton's second law, force equals mass times acceleration. So if you have a mass of 3 kilograms and it's accelerating at 9.8 meters per second squared, so it's falling, say, and it falls for 4 meters, how much work was done on the object? So go ahead, pause the video, calculate that, and then check your answer. You should have gotten 3 times 9.8, so that's your mass times acceleration, which is your force, times 4 meters, so 3 times 9.8 times 4. I have the 3 and the 9.8 in parentheses, but they don't have to be. It's multiplication. It doesn't matter in which order you do it, but then you end up with 117.6 joules. So we say there was 117.6 joules of work done on that object. Notice that if you have no distance, there would be no work done on that particular object, and we'll talk about that a little more in class. So breaking down the unit of joules, as you can see, a joule is kilograms. Kilograms comes from the mass, times meters per second squared, which comes from the acceleration. Mass and acceleration is your force, times meters, which is your distance. So if we multiply this all together, we get kilogram times meters squared over seconds squared. And that's what a joule kind of breaks down into with your kilograms, meters, and seconds. The next concept we have is power, and that's Chapter 6, Section 2 in your book. Power is the rate at which you do work. So it's a rate, which means we would expect it to be something divided by time, and it's in fact work divided by time. So if you do 400 joules of work and you do that in 30 seconds, go ahead and calculate your power. Your power should be 400 joules divided by 30 seconds is 13.3 watts, and watts is the unit that we use for power. So here's another problem. Let's say you're rearranging your room and you push your 50 Newton bookcase 2 meters in 5 seconds. So first let's look at how much work you do on the bookcase. You should have gotten work equals force times distance, which is 50 newtons times 2 meters. You've done 100 joules of work. So now let's calculate how much power you did moving the bookcase. So go ahead and calculate that and then check your answer. Power is work divided by time, and so that's 100 joules in 5 seconds, which is 20 watts of power. So now let's say after you've done all of this work, you change your mind and you move the same bookcase back to where it started. But this time you're tired, so it takes you 10 seconds instead of 5. So compare the work and the power done. Go ahead and pause, compare those two, see how they're different, see how they're the same, and then check your answer. You should have found that your work is exactly the same. You've moved the same distance, or you've moved something the same amount of force over the same distance. So you still have a work of 100 joules, but your power, it took you twice as much time, so your power is cut in half. We can say that power and time are inversely proportional to one another. And that makes sense. The longer it's going to take you to do something, the less power you have. That kind of makes sense in your head. So the next thing we're going to look at is kinetic energy, and kinetic energy is in 6.3 and 6.5 of your book. Potential energy is in 6.4, so you want to look at that whole 6.3 to 6.5 kind of span for kinetic and potential energy. And kinetic energy is 1/2 times mass times velocity squared. And so, for example, what is the kinetic energy of a car with mass of 100 kilograms traveling 3 meters per second? Go ahead and calculate that. You should have gotten kinetic energy is 1/2, and 1/2 is just a number that we use when calculating kinetic energy. So it's 1/2 times 1,000 kilograms times 3 meters per second squared. The 3 meters per second is the part that's squared. So that's essentially 0.5, which is 1/2, times 1,000 kilograms, times 9, which ends up being 4,500 joules. If we want to look at how this unit breaks down, we see it's kilograms from the mass, the 1/2 has no unit, times meters per second, which is squared. So that's kilograms times meters squared over seconds squared, which is kilogram meter second, meters squared over seconds squared. Exactly the same thing we found when we calculated work. So we see that this unit of joules is the same regardless of what we're calculating. Looking at potential energy, that's GPE, and it's mass times the gravitational acceleration times height, and that again is 6.3 and 6.4 in your book. Another way of looking at that is GPE equals weight times height, because weight is mass times gravity, or the acceleration from gravity. So what's the GPE of a 0.5 kilogram book on a shelf 1 meter off the floor? You would calculate GPE equals 0.5 kilograms times 9.8 meters per second squared, we're assuming this is on Earth, times 1 meter, which equals 4.9 joules. So what would happen if we moved the same book to a shelf 2 meters off the floor? So I took it from the shelf 1 meter off the floor and I moved it up a meter. And so there we calculate GPE as 0.5 kilograms times 9.8 meters per second squared times 2 meters, which gives you 9.8 joules. And in this case, the book now has double the potential energy, which makes sense. But one thing I want you to think about is, where did that energy come from? It seems to have picked up 4.9 joules of energy. Later we'll learn conservation of energy tells us something must have lost 4.9 joules of energy. So what is that? And so finally we look at the unit again. So GPE is kilograms, that's your mass, times meters per second squared, that's your acceleration from gravity, times meters, that's your height. So once again we find that the joule is a kilogram times meters squared divided by seconds squared. So you can see all throughout a joule is a kilogram meter squared per second squared. So now that you've gone through all these examples, kind of determine your level of comfort with them and then download level 1, 2, or 3 of the calculation sheet.